Hello, hello, hello. Uh, I'm so sorry, guys. I literally had, I don't know if you can hear me. Can you hear me? I literally have my my earphones are broken. Hello, hello, hello. Now they're working. Guys, I'm so sorry. I've been like talking about 20 minutes without it. What happened was is my earphones, my headset was unplugged. It ever so slightly, but enough that it was off. But I saw a signal at my end. So, okay. You know what? Let me see if I can just go over this stuff very quickly. I don't want to waste too much of your time. And I apologize. You know, I should have looked over at the chat a lot earlier. And let's take a look here. Okay, so we're just going to go very quickly over this stuff. I think, though, you might have been able to figure out some of the things what I was doing just because I was, um, uh, you know, doing it. But all right, so very quickly, I think this will take me about 5 minutes. I apologize again, and I should be more careful in the future. Okay, so the first one was intensity can be measured in watts per meter squared. Okay, and because intensity is in 3D, the sound spreads out. It actually does a decreases 1 over r squared. And so I have a question like if the intensity of a bell of like one bell is at 3 meters is 15 milliwatts per meter squared. At 5 meters, what is it? Well, you just simply say, well, you know what? At 1 meter, I'm going to just sorry, at the 3 meter mark, I'm going to take that to be the 50 milliwatts. That's your subscript 1. I2 is what we want to solve. R2 is 5 meters. You plug into the formula, which I will just rewrite here very quickly. You rewrite into this formula here like that, and you substitute it, and you get that it's 18 milliwatts per meter squared. So there's an example of an inverse R squared law, okay? And ask yourself, does that make sense? Well, if at 3 meters it's 50 milliwatts per meter squared, then at 5 meters it's got to be less, and it is. Okay, there we go, inverse R squared. Let me know if you want me to slow down, because I think, you know, some of the stuff is easy enough, and I think you'll probably figure it out from just my quick discussion of it. Okay, so now this one is an even easier one. Okay, this one is meant to be contrasted with what I did later. Okay, so if you have one bell which has say 37 milliwatts per meter squared at a given distance, what's the intensity of 5 of those bells? In watts per meter squared, intensity is linear, which means that all you have to do is multiply by 5. It's really that simple, but that's only in watts per meter squared. So the intensity of 5 bells is going to be 5 times 37, which is the 185. Okay. Now, the reason I gave you this very simple problem here is to contrast what happens when I give you the intensity in terms of decibels. Okay. So in decibels, this is the conversion. That converts between that converts between your intensity in watts per meter squared, which is I here, and your decibels beta. Okay, I naught is a reference, and it's simply that number there. And I recommend that when you guys do your like study, write down the equations, write down the constants with them, because it's open book. You're going to be able to just read the constants, but you don't want to go shuffling through your notes, so just have them written down for yourself. Okay, all right, so what's the intensity of 37 milliwatts per meter squared in decibels? If you use this formula here, you can convert back. Okay, so the 37 milliwatts per meter squared, that's your I. There it is there. Okay, the I naught, that's this. Okay, the milliwatts, the milli is the 10 to the minus 3. And then just working this through, you get that beta is 106 decibels. Okay. Now, the other way, I could ask you to go the other way. If I give you 85, convert to I, well, you put that in there. Okay. And of course, there's a 10 in front here. So 85 divided by 10 will give you 8.5, and that isolates the log. Okay. And of course, I naught is 10 to the minus 12. Okay. Now what? Well, you want to solve for that I, which is inside the log. And so you make use of this property that if you have a is equal to log b, that means 10 to the exponent a is equal to b. That's because log and exponentiations are inverses of one another. And so if I exponentiate this side, that's going to be, it's 8.5, so it's going to be 10 to the 8.5. And on the other side, the log just goes away. Okay, so now I'm going to multiply both sides by 10 to the minus 12. So 10 to the 8.5 times 10 to the minus 12 gives me that number right there. Okay, and on a test, I would probably convert that to milliwatts. And so that's 0.316 milliwatts per meter squared. All right. Okay, so far so good. I don't see anyone complaining in the chat. And let's go on. Okay, when it comes to decibels, it is wrong to do what we did here. Okay, which is just multiply. All right, here, same kind of question. One bell has an intensity of 40 decibels. What's the intensity of 5 such bells? Don't just multiply by 5. That's wrong. Okay, what you do is go back to this formula and you say, you know what? Let me write that formula. Now, it's originally the formula is this, but say, let me apply it to just one bell. So I'll call that beta 1 and I1. Beta 1, I told you, is 40. Okay, so you say, well, what's it going to be for 5 bells? Well, for 5 bells, let's call that beta 5. It's going to equal this. But now that I1, it's not just one I1, it's 5 I1s, like that. Okay, so there's 5 of them because we got 5 bells. Now, that 5 is inside the log. And there's this property of the log that if you have two numbers that are multiplied inside the log, so log of A times B, that's going to turn into log of A plus log of B, like that. Okay, and so now you get 10 log 5. That's going to be one term. And then the other term is going to be 10 log I over I naught. There's your second term. And you say, well, why'd you break it up that way? Because 10 log I1 over I naught, that's back to your beta 1. And so there's beta 1 there. So beta 5, which is the intensity in decibels of 5 of them, is going to equal 10 log 5 of just one of them. 10 log 5 turns out to be 7 plus 40, that's 47. Okay, so to summarize, one bell has an intensity of 40 decibels. Multiply that by 5. 5 bells will have an intensity of 47. 25 bells, where did I get the 25? Multiply by 5 again. That's going to be 47 plus another 7. Okay, that's going to be 54. And then 125 bells, again, 25 times 5 is 125. That's going to be 54 at 7, and that's going to be 61 decibels. So every time you increase the number of bells by multiplying by 5, so you've got 5 times more bells, you're going to have an intensity which is increased by plus 7. Okay, and we're all caught up, and I did it in, I lost like 7 minutes there. Okay, so can people in the chat just let me know, was that all okay? Did I go too fast over any of that? Let me just see here, everything okay? If I hear nothing, then I'll just continue. All right, one more topic with sound, and that was the Doppler effect. And here's the formula here. Okay, and with the Doppler effect, what's happening is you've got a sound source, and you've got also an observer, someone that's listening to the sound. And if the sound source and the observer are not moving, both of them are not moving, then you're going to hear a certain frequency, okay? And that's your F naught, okay? So F naught is the frequency that's heard if neither the source nor the detector is moving. But if either the source or the detector are moving, you actually hear a different frequency, and that's the frequency that's heard, F, like that, okay? And it depends whether the source is moving or the receiver is moving, okay? And so let me just do a couple of questions here. So let's say a car horn has a frequency 750 hertz, like that, when standing still. Okay, what frequency does a stationary detector here, what does a stationary detector hear when the car approaches at I don't know, 30 meters per second? Okay, so there's our first question. Okay, so let's see here. All right. Okay, so a car horn has frequency 750 hertz when you're standing still. So F naught is going to be 750 hertz, like that. Okay, so that's the frequency that's heard when everyone's standing still. Okay, now What frequency? What frequency does a detector hear? That's your F. That's what's unknown. You don't know what frequency is going to be heard. Okay. Now the V here in this formula, that's the speed of sound. Okay. The speed of sound is 340 meters per second. Okay. All right. The VR is the velocity of the detector. Okay. What frequency does a stationary detector? Okay. So we better be careful here. R can be the word R. The subscript R could be receiver. Sometimes you'll hear me say detector. Sometimes you'll hear me say observer. Basically anything that's receiving the sound. Okay. Well, it's stationary, so that velocity is 0 meters per second. Okay. And Vs is the source. Okay. And that's the car. And the car is approaching at 30 meters per second. And so there we go. All right. Now we're almost ready to plug into this. The only problem you have to watch out for is you'll see there's a plus minus there and a plus minus there. Okay. And that plus minus depends on whether the source is actually approaching or moving away from one another, whether it's the source or the detector. Okay. So in this case, it's the source that's moving. So let's plug in and see what happens. Okay. So that V, that's the 340. Okay. Because that's the speed of sound. The receiver is 0. Okay. Now, whether you have 340 and you subtract 0, you have 340 and you add 0, it doesn't matter. That's going to just drop out like that. Okay, so we don't have that plus or minus in the numerator, doesn't matter. Over here we have Vs, that's the source, that's 30, and now you have to ask yourself, do I want to add or do I want to subtract? Okay, now the way I do it in my mind is I say, look, if the source is approaching the receiver, it's going to go up. So imagine that you're on, like a car is approaching you, okay? And everyone's heard this Doppler effect. The car is approaching you. The frequency is higher as the car approaches, and it drops when it recedes from you, okay? And so you say, well, I have to choose the sign that gives me the higher frequency because the car is approaching, okay? So as the car approaches, all right? And you say, well, if I do the plus sign in there, you'll actually get a lower number. So you need the minus sign. Okay, like that. That's the way I figure it out. I say, well, what sign do I need such that I get the right, so that the frequency shifts in the right direction? And the other one, if not, that's 750 like that. Okay, and so this is going to give me a frequency of this number right here, and it'll round up to 823 hertz. Okay, looking in the chat here. Well, no one answered my question, so I'm assuming that everything is okay and you can hear me. All right. So there's the situation when the car is approaching. Let's change things around a bit. So let's do this problem again. All right, like that, and recedes at 30 meters per second. So, oh, wait a sec. Yeah, no, that's right. So at the end, ask yourself, does it make sense? Well, you were 750 hertz and it's approaching, so the frequency has to go up. So 823, that's correct. Okay. Now, what happens if the car recedes? Okay, recedes. No, I was spelled right. Okay, recedes. Well, it's the same formula, okay, but now, and the same substitutions, but now, when we had that plus minus in there, we want the frequency to shift down. And the minus makes it shift up, so we are going to add this time. And if you calculate it now, you're going to get a number lower than 750, which is 689 hertz, like that. Okay, so just remember, when the source is approaching, the frequency is going to shift up. So 750, that shifts up to 823. When it's receding, the frequency is going to shift down. So it started at 750 and it shifted down to 689. Okay. Now that's a story if the source is moving and not the receiver. But if you think about it, it's not that different. What would be different here is if I go back to this formula here. I don't want to do too many of these problems. Okay, but if you go back to this formula right here, there it is. Well, you know what? Maybe just one more. very quickly. It doesn't take that long. So we'll do this, copy, paste. So 750 what frequency does a stationary car, or what frequency does a receiver hear when it is approaching at 30 meters per second? Okay, and I guess just to be clear, while the car is stationary. Okay, so what's changed now? Well, now if you go back to these numbers we had right here, okay, the stationary frequency is the same. It's still 750. Okay, the frequency, the shifted frequency, is what we want to calculate. Okay, the speed of sound is the same. The receiver now is moving at 30 meters per second, and the source is stationary. Okay, so if we take this formula here, like that, and we substitute in, okay, V is 340 and 340, like that. The source is now 0 because the velocity of the source is 0 because it's not moving. So this goes away there like that. Okay, of course the stationary frequency is still 750, like that. And now you have to figure out, what do I do here with VR? Well, it's 30, but do you add or subtract? Okay, well, if it's approaching, the frequency shifts up. Okay, it doesn't matter whether it's the source is approaching or the receiver is approaching. As long as the distance between the two is decreasing, the frequency is going to shift up. And so you say to yourself, well, if I put a minus there, will it shift up? And the answer is no. So you want the plus in there. Okay, so if you do that and you put a plus in there, you'll get a higher frequency now. And that number is 816, okay, hertz. Okay, so it shifted up. All right, now in this case, the receiver was approaching at 30 meters per second and we got 816. In the previous case, it was the source that was approaching and we got 823. So it does matter whether it's the receiver that's moving or the source that's moving. Okay, even if they're approaching one another, if it's the receiver that's approaching, you'll get one answer. If it's the source that's approaching, you'll get a different answer. Okay, so I think we've done enough with examples of Doppler shift. Let me take a look in the chat here, and okay, looks like people are not complaining, and I'm feeling a little bit paranoid, and the reason is that my levels on my end, even when you weren't hearing me, the levels at my end were good. Okay, but apparently, there was a problem. So okay, let me just before I go on, the next topic is thermodynamics. Before I go on though, let me just repeat, go back to the browser here, and let me just because you didn't hear this at the beginning, what's covered on the test. Okay, so this is the very first thing I did. What's covered on the test, just to be very clear, is going to be sound, thermodynamics, and electricity. You can even say it's an introduction to electricity. So it's just those three topics. The voltage, current, resistance, capacitance, that's not covered. Okay, I just wanted to be clear about that because you didn't hear that part. All right, let me see here. No questions so far. All right, the next topic is thermodynamics. Okay, and for thermodynamics, we had quite a bit. All right, it was a longer topic, and we had first the thermometer formula, and here's this thermometer formula. What it basically says is that an object will expand if there's a temperature change. Okay, so if you take a look here, if there's a temperature change, that's going to lead to a corresponding expansion. Okay, so the delta T is the change in temperature. It's like that. Okay, oops, right here. Well, why can't I paste? There we go. Okay, it's the change in temperature. It's like your higher temperature minus your lower temperature. Okay, like that. So it's a change in temperature. The delta L is a change in length, and that L naught is kind of like your reference length. It's like your length at T lower, like that. Okay, and so your delta L is actually going to be equal to the length at the higher temperature, okay, minus L naught. All right, so this is sometimes confusing, or people make mistakes there because they think of L as the length, or delta L as the length. It's not, it's the change in length. Okay, so let's do a problem with this, it's like a problem like in your assignment. Okay, so an object or a bar has length, I don't know, 30 centimeters at negative 20 degrees Celsius and 35 centimeters at 80 degrees Celsius. Okay, find alpha, and alpha is your coefficient of linear thermal expansion. Okay. Oh, and I got to tell you, a bar. No, I did tell you 30 at that. Okay. All right. So find that. All right. So the delta L, what is that? Well, let's start off with L naught. L naught is the length at the lower temperature. Okay. And the lower temperature is the minus 20. And so L naught is going to be 30 centimeters like that. Okay. Delta L is going to be the length at the higher temperature minus the length at the lower temperature. So the higher temperature is 35. The lower temperature was 30 centimeters like that. And that means that the length expanded by 5. Okay. So think of the delta L as how much did the thing expand? Not what is its length, but how much did it expand over that temperature range? Okay, so now what? Well, that gives us, now we've got L naught, we've got delta L. What's the delta T? So the delta T here, just rewrite this, it's the higher temperature, which was 80 degrees Celsius, and the lower temperature, which is negative 20 degrees Celsius, like that. Okay, now you got to be careful here. I've done quite a few problems like this where you have the lower temperature is negative. It's going to be negative, a negative number. So that turns out to be 100 degrees Celsius. Okay. So if you go from negative 20 to 80, you say, well, how much did you increase? Well, from negative 20 to 0 was 20, then another 80 to get to 80. So the total change in temperature is 100 degrees Celsius. Okay. So great. There's your delta T. And now what? Well, now we could just go back to this formula here. All right, rearrange it so that alpha is isolated. So that would mean that you'd have alpha is equal to, divide both sides by L naught delta T, like this. Okay, and your delta L we found was 5 centimeters. Your L naught we found was 30 centimeters, like this. Okay. And the delta T was 100 degrees Celsius. And I guess I should just put a little multiplication symbol in there like that. Okay. So there it is. So delta L, it expanded 5 centimeters. L naught in the denominator was 30 centimeters. And also in the denominator is delta T, the change in temperature. That's 100 degrees Celsius. Okay. And what's that going to equal? Well, let me just write this without the units so I can cut and paste into my calculator here. And it is this number right here. It's equal to that. Round that off. Let's round it off. There we go. Like that. Whoops. Okay. The units is, notice the degree Celsius is in the denominator, so it's going to be per degree Celsius. I know that's a funny unit, but there it is. Okay. So there's our alpha. Let me just write it all in one line. There's our alpha there, like that. Okay. It is a measure of how much expansion you get per degree Celsius. Okay. So now what? Okay, so that's one question. Find the linear expansion. What is the length of the bar at 0 degrees Celsius? Okay, so how long would you expect it to be? Well, if it's at 30 at negative 20 and 35 at 80. You expect it to be longer than 30 but less than 35. Okay, you say, well, how do I calculate that? Well, what you do is you calculate, starting from this formula right here, you calculate how much it expands. Okay, and so let's calculate that first. So delta L is not the answer. Delta L is how much it expanded over the 30. So alpha, do we know alpha? Well, we do now. Okay, alpha is this quantity right here. All right, and L naught is the 30 centimeters. And delta T is, what's delta T? So delta T in this case, let me do it over here. Just this. Think of it not so much as the higher temperature and the lower temperature, but the change in temperature. Okay, so the lower temperature, that's still negative 20. Wow. So it's going to be the higher temperature minus the lower temperature. The lower temperature here is still going to be the minus 20. That's like the lower temperature is like our reference temperature. Where is it? Here we go. Okay. So the lower temperature is that, but now the higher temperature is going to be 0 degrees Celsius. Okay, because we want to say, well, how much did it expand in going from negative 20 to 0 rather than all the way up to 80? Okay, and so that's going to be negative here. That's going to be just 20 degrees Celsius, like that. Okay, so I hope that wasn't confusing, but maybe we should just take out the word higher there and just say the temperature that we're interested in this case 0 degrees Celsius. Okay, and minus the lower reference temperature, minus 20. That's a change of 20 degrees Celsius. Okay, like that. All right. So like just like there's that L naught there, which is the reference length. Inside of delta T, there's the reference temperature, the lower temperature. Okay. Now, if you work this out, what's that going to equal? So it's this number here. By the way, notice that per degree Celsius there cancels that. Okay. And the only remaining unit is going to be centimeters, like that. So the answer will come out in centimeters. All right. So let's cut and paste this into my calculator. And I get that it's equal to this number right here, which rounds off to 1 centimeter. Okay. Now that can't be the answer, 1 centimeter. Delta L is 1 centimeter. The change in length is 1 centimeter, but that's not how long the bar is. The bar started at 30 centimeters and expands to 35. So basically what this is saying is the length is going to be 30 centimeters, but then it expands by 1 centimeter, giving you 31 centimeters. And that's the answer. At 0 degrees Celsius, the bar is 31 centimeters long. Okay, so let me take a look here in the chat. All right, there we go. All right, so the opposite of this is I could say to you, instead of asking what's the length, I can say, what is the temperature when the bar has length and let's say 32 centimeters. Okay, so same formula like right here. All right, but now let's be careful. So delta L is how much did it expand over the 30 centimeter mark? Well, it started at 30 centimeters, so that's your lower length, but it expanded to 32 centimeters. So the total expansion in this case is going to be 2 centimeters. Okay, remember delta L is the change in length, not the actual length. Okay, starts at 30 at minus 20 and it expands to 32 because I told you that. Okay, so we've got that. Alpha, well, you know that from above. L naught, that didn't change, that's still 30. The delta T now, how should you think of that? Well, the delta T is the temperature that we're interested in minus the reference temperature, which is minus 20 degrees Celsius, like that. Okay, so that it's that T there that we actually want to find. All right, let's do it in 2 steps. We'll start with this and we will isolate delta T. Okay, so divide both sides by alpha L naught, like that. And we get that delta T is equal to delta L divided by alpha and L naught. Okay, so your delta T is going to equal this. I'm just rearranging it so it's easier to read. How much did it expand? What's your delta L? Well, it expanded 2 centimeters over the reference. divided by your alpha, which is this number right here, multiplied by your L naught, which was 30 centimeters. Okay, put a little multiplication sign in there. Okay, and this answer now, the centimeters will cancel out because there's centimeters here and there's centimeters there, so they'll cancel. And the units of alpha were per degree Celsius, so the answer will come out in degrees Celsius. Okay, so if I take this and multiply it out, I get 39.9. Okay, now that's your delta T. That isn't your final temperature. That's how much the temperature increases over your reference temperature. Okay, think of that as this. Oops. Okay, so now what your temperature is actually going to be the 39.9, which is how much it increased over the 20 degrees, like that. Okay, and so your answer turns out to be equal to 19.9 degrees Celsius. Okay, so let me explain what I did here. Maybe I went a little bit fast. You start at negative 20 and you increase 39.9, say 40. So actually, let's do that. Let's round that off to 40. Okay, let's round that off to 40. It's a little bit off, but at least it helps you to see. So you start at negative 20. If you're at negative 20 and you increase 40, where do you end up? You end up at 20. Delta T is not the temperature, it's how much the temperature increased over your bottom temperature, which was negative 20. And so the temperature will be 20 degrees Celsius. So when the bar has length 32 centimeters, the temperature is 20 degrees Celsius. All right, let me see if there's any questions in the chat. Okay, is everyone doing okay? All right. Yeah, I'm looking over a little bit more often now because in case this problem happens again, I wonder if it's because maybe I accidentally sat on the plug for the speaker. Thanks, Matt. Yeah. All right. Well, let's continue. I mean, this is going to be a probably a 2-hour stream, but there's a lot of material in this section, which is why I didn't add that extra part on voltage, okay, and currents and so on. Okay. Let's continue. So the next thing we did with thermodynamics was PV equals nRT. So this formula here, where is it? This formula right here for a thermometer, it's not totally accurate. It's it kind of works if delta T and delta L are small, but if you start to get larger temperature changes, you get larger length changes, it turns out that the linearity breaks down, okay, for reasons that I discussed during the lecture. But there are gases which are linear over large ranges, okay, and that leads to the ideal gas law. Okay, so there's the ideal gas law. There's two forms. PV equals nRT is the way it's usually written in chemistry, where R is the ideal gas constant. There it is. Okay, again, write that constant down when you're studying for the test, so you don't have to waste time looking it up. Okay, the other form, which is a little bit more popular in physics, is PV equals N K Boltzmann T. So that K in there, I didn't put the B there, but it's actually like K Boltzmann, like that. Okay, so it's K Boltzmann. It's called Boltzmann's constant, and it's basically a conversion factor between I guess I can put the B in here like that. It's a conversion factor between energy in joules and temperature in Kelvin. Okay, and in solving problems with PV equals nRT or PV equals NK Boltzmann T, make sure that your temperature is in absolute in Kelvin, okay, in an absolute scale. All right, and the reason is that when the temperature goes to 0, the volume should also vanish. Okay, if you're working in Celsius, 0 degrees Celsius is water freezing. Well, volume doesn't vanish at that point. I mean, the atmosphere doesn't vanish at 0 degrees Celsius. That would be a rather strange world. Okay, so the 0 there has to be in Kelvin, and the conversion's pretty easy. Maybe I could just write that off to the side here. 0 degrees Kelvin is basically minus 273 degrees Celsius. Okay, that's how you convert. All right, well, let's do a quick problem with this, and let's do two. We'll do one with this and one with that one. Okay, so let's start off with this one just to be a little different. Okay, so how many particles of a gas are there in I don't know, 55 liters and 55 liters at 1 atmosphere pressure and temperature. What should the temperature be? Let's make it 30 degrees Celsius, like that. Okay, so there we go. So how many particles? Well, the first thing is, why didn't I say atoms or molecules? It doesn't matter. Whatever the gas is made out of, doesn't matter. That's your capital N. Okay, so if I'm asking how many particles, you want to use this form right here. Okay, if I'm asking for how many moles, you're going to be using that form there, because N is number of moles. So we want it in this form here, like that. And we're solving for N, capital N here. So what we're going to do, let me just move this to the other side like that. Okay, I just flipped it around. Okay, so we want to solve for capital N, so divide both sides by K Boltzmann T, like that, and then we can solve for N. All right, so we need the pressure, and the pressure, I tell you, is 1 atmosphere. But we need everything to be in MKS, okay? Because if you don't use pascals here, then the conversion factors here won't work, okay? So 1 atmosphere, you go, well, what's 1 atmosphere in pascals? And the answer is 101.3 kilopascals. That's not MKS yet. Pascals is MKS. It's kilo. This is just the way it's usually written in the notes, or if you were to Google online, what's the 1 atmosphere in pascals, it would probably say 101.3 pascals, but we got to work in, kilopascals, we've got to work in pascals. So that would be 101,300 pascals, like that. Okay, so there's 1 atmosphere. Okay, well, you know what? Let me change it to 2 atmospheres. If it was 2 atmospheres, what would you do? You just do 2 times that. Okay, all right, so it'd be 2 times that. Okay, so there's your, I'll work that out very quickly here. I just changed it because I didn't want to make it a trivial like 1. Okay, so every atmosphere is 101.3 kilopascal. So if you have 2 atmospheres, well, then multiply by 2. Okay, all right, what's the volume? Well, the volume is 55 liters, but you want the volume in what? Meters cubed. And you go, well, what's the conversion? It turns out that it takes 1,000 liters to make 1 cubic meter. Okay, so it's going to be 55 divided by 1,000, like that. All right, and so that's going to equal 0.055 meters cubed. All right, so liters are popular in chemistry, but in physics, because we're working in MKS or meters cubed, just divide by 1,000. All right. And what do we need now? So we need the temperature. That's the next one we need. And the temperature, I tell you, is 30 degrees Celsius. But what? You don't want to put 30 degrees Celsius in there. You want to convert to Kelvin. So you just take 30 and you add to it 273 Kelvin. Okay? And degrees Kelvin, like that. All right? And so what's that going to equal? That's going to equal 303 degrees Kelvin. All right? So now we're ready to plug in. P here, for P we're going to put in this number right here. Whoops. Okay. For the volume, we're going to put in this number right here. For K Boltzmann, we're going to put in this number right here. 1.38 times 10 to the minus 23. And for the temperature, we are going to put in 303. All right. And what does this work out to? Your answer should be somewhere in the range of like 1 mole. Okay. Not exactly, but somewhere in that range. Okay. And this is the number I'm getting. It's actually a little bit more than 1 mole. It's that. Okay. Or let me round that off. 2.45 times 10 to the exponent 29. Okay. Oh, that's wrong. 1 second, that's wrong. It's wrong because I accidentally multiplied rather than divided there. Okay. I cut and paste incorrectly. There we go. And now it's also like way off, like from 1 mole. There we go. There's the answer, or rounding it off, it's 2.66 times 10 to the exponent 24. Okay. Now remember, Avogadro's number is like 6 times 10 to the 23. Okay. Now it's not going to be exactly that because I just made up those numbers. But you're expecting whenever you're asking a question of like a macroscopic number of particles, atoms or molecules, you're expecting something in the vicinity of 10 to the 23, 10 to the 24. Okay, and there you go. So it's 2.66 times 10 to the 24. Whatever the atoms are. Okay. You see here in the chat. Okay, we're good. Let's do another one of these problems. And let's do one that makes use of this. Okay, so let's say here's one where you don't have to convert. Okay, so a gas at temperature 50 degrees Celsius and pressure. Oh, you know what? I'm going to use some crazy units. Don't worry, you'll see that the units don't matter. 500 torr occupies 750 cubic centimeters volume. At this point, you're going, wow, that's some pretty crazy units. What's a torr, and what's this? Okay, so I did mention torrs early in the course, but 760 torrs is 1 atmosphere. But that's not important. You're going to see that the units here actually don't matter as much. Okay, this gas. In this particular problem, this gas is transferred into another container of volume 255 cubic centimeters and pressure. This gas is transferred to another container, period. The pressure is found to be 1,300 torr. What's the temperature? Okay, so let me reread the problem. So we start off with a gas. It has a temperature of 50 degrees Celsius, a pressure of 500 torrs, and it occupies 750 cubic centimeters volume. Okay, the gas is going to be transferred to another container which has a volume of 255 cubic centimeters. The pressure now is 1,300 torrs. What's the new temperature? And you go, whoa, how do you solve a problem like this? Well, let's start with this equation right here. Okay, and let's say we have a before situation with a P1, which is the original pressure is 500 torrs. Okay, a V1, which is 750 cubic centimeters, and a T1, which is 50 degrees Celsius. This one we absolutely must put into into Kelvin. Okay, so that's going to be plus 273, and that's going to be 323 Kelvin, like that. Okay, degrees Kelvin. All right. All right, so there's the before situation. The after is going to be P2, which is going to be 1,300 torrs, V2, which is equal to 255 cubic centimeters, T2, which is unknown, because I didn't tell you, I'm asking for it. And you go, geez, how do I solve this? Well, take a look at this equation here. I can write it twice. I can write it once for the before situation, P1, V1, NR, T1, and I can write it again for the after situation, P2, V2, T2, like that. Okay? Now, the N is the same because the N is the number of moles, and it's the same gas. It's not like I added gas or I removed gas, so they're the same. Okay, so let me divide both sides by T, on this one, let me divide both sides by T1, so I'll have divided by T1 here. And let me divide both sides here by T2, like that. And notice what we have here. We have these two equations. but the right-hand side of both of those equations, that NR1, sorry, the NR, is the same. And so we could just set this side equal to that side. Okay? I mean, you could memorize the equation that way if you like. All right, but for these particular problems where you have like the same gas, so you're not adding gas or removing gas, and you know the initial state and you know the final state or part of the final state, and you want to calculate one of the three quantities in the final state, pressure, volume, temperature, you can use this form right here. Okay, now the reason you didn't have to convert to MKS is because let's start plugging in. So for P1, we're going to put in, let me just rewrite this. For P1, what are we going to put in? Well, P1, 500 torr. Okay. V1, 750 cubic centimeters, like that. T1 was 323, like that, Kelvin. There we go. Okay. P2, that's going to be 1,300 torr. V2, that's going to be this, 255. And T2, that's our unknown. Now, notice I put the units in here, and I did it on purpose because they're not MKS units, but look at what happens. See the torr on this side? They cancel the torrs on that side. Okay? And see the cubic centimeters here? They cancel the cubic centimeters there. Okay, and the only remaining unit are degrees Kelvin, which is of course what you want because the answer has to come out in Kelvin. Okay, so if I take this equation and I multiply both sides by T2, that'll get rid of the T2 down here, like that, and divide both sides by, well, let me do it in two steps because I don't want to confuse things. Okay, so you know what? Let's go back. I wouldn't say I'm being lazy, but I think I'm economizing a little bit too much. So let's see what this is going to equal here. Okay, on this side we have that. It actually rounds up like that. So that's this quantity here. And then this quantity here is going to be there, like that, divided by T2. Okay, now multiply both sides by T2 and divide both sides by 1,161, and that's going to give us a temperature of that, and it'll round up to that. Okay, degrees Kelvin. Okay, and so there's the answer. But if I wanted this in Celsius, what is this in Celsius? Well, it's going to be 286 is going to equal, or minus 273 is going to equal 13 degrees Celsius. Okay, so there's the answer in Celsius. Okay, either 286 degrees Kelvin, or 13 degrees Celsius. Okay, let's take a look in the chat here. All right, I think we've pretty much exhausted the PV equals nRT problems. Okay, I did want to show you this particular little trick right there. It's a nice little trick that helps you to solve the problem quicker. Okay, you could start with this, calculate your N, and like use this and then calculate N, and then do it again. And calculate the temperature, but it's much quicker to do it that way. Okay, and I did an example like this in the pre-recorded lecture, and I might as well show it here as part of the review. All right, okay, let's continue here. So what did we do next? Well, the next thing that we did was we looked at specific heats. Okay, so specific heats were and latent heats. Okay, specific heats are the heat that it takes to heat up to raise the temperature of a material. So you have water, and say it's water at 20 degrees Celsius, and you want to warm it up to water at 40 degrees Celsius. You say, how do you do that? You put energy into it. Okay, remember, heat is just the diffuse kinetic energy of the particles that are moving around in there. You don't see them moving around. Like, I pick my phone here and I say, look, do you see the molecules moving around? Of course not. They're very small, but they are. They're bouncing around with quite a bit of energy. Okay, and if you add up, all the energy of the kinetic energy of this one molecule, plus the kinetic energy of the next one, plus the kinetic energy of the next one, plus the kinetic energy of the next one, well, it's going to add up to a certain amount. Okay, now if I take my phone and I just rub it, I warm it up with some friction, then what I'm doing is I'm speeding up the molecules a little bit. I'm adding some energy, and that corresponds to the temperature, because the temperature is the average kinetic energy. That corresponds to the temperature increasing. Okay, so actually, you know what? I forgot to do a problem. Before we get to this, we should do a problem with this right here. Okay, so actually what I said is not incorrect, but the average kinetic energy being related to the temperature, and that are actually very closely related. So let's just do a very quick problem with that. Okay, what's the average kinetic energy of I don't know, the molecules in my phone at 20 degrees Celsius? Okay, so what is the average kinetic energy of particles at 20 degrees Celsius? Okay, and the answer would be, take that. Okay, so for K Boltzmann, we are going to put in this number right here. Whoops, I went too far. There it is. And the temperature is going to be, this has to be in Kelvin as well. So it's going to be 20 plus 273, like that. Okay, and that's going to equal why is it giving me 0? Oh, I think I know why it's giving me 0, because it's rounding off in a stupid way. Okay, my calculator. Okay, so it'll be 606 times 10 to the negative 23, and that would be in joules. Oh, okay, let me see. Can you see that? Yes, you can. Okay, and so then the kinetic energy here would be equal to, if I just move the decimal over 2, it would be 6.07 times 10 to the negative 21 joules. Okay, so the average kinetic energy of particles, and it doesn't matter what particles they are, whether they're in a gas or whatever, they're going to be like 6 times 10 to the minus 21 joules at 20 degrees Celsius. Okay, now I should say there's some complications depending on whether they're monatomic or diatomic molecules. Okay, that's a very small kinetic energy because molecules are very small. So what happens if you have like usually we pick on helium? Okay, so let's do that. What's the average? What average velocity does this correspond to for helium? And the mass of helium is 4 atomic mass units. Okay, well, 4 atomic mass units, you say, well, what is that? An atomic mass unit, to convert it to kilograms, this is the conversion factor right here. Okay, let me put it in brackets. All right, and whoops, that should be 10. And you could just look this up in our notes. Okay, so 1 atomic mass unit is equal to 1.67 times 10 to the minus 27 kilograms. Okay, now helium, the nucleus, the electrons don't really contribute much to the mass. The nucleus is made up of 2 protons and 2 neutrons for a total of 4, and each one of them has this mass there, and so there's the answer. Now, I wouldn't expect you to know that. I would just tell you, how many atomic mass units there are, okay, in the material. Probably helium, you should know. Everyone should know that it's 4 AMU, okay, but there's other materials, you go, well, what's the atomic mass for them? I wouldn't expect you to know, but basically, this turns out to be, oh, it's doing it again. Let's do it this way. 6.68 times 10 to the negative 27. Okay, kilograms. That's how much a helium atom weighs. Okay, you say, well, why did you do that? Well, because that kinetic energy there can be expressed in terms of the velocity as 1/2 mv squared. Okay, from last semester, kinetic energy is 1/2 mv squared. And so if you know the kinetic energy, it's this number here. Okay, and well, the half is just 0.5. You know the mass, that's this number right here. Okay, and you've got a v squared like that. Okay, now you can solve. Okay, so let me solve this. My calculator is being a little bit funny with exponentiation, so it's going to be times this, multiply both sides by that to the positive 27. Okay, because that would get rid of that, and then divide by this. Okay, all right, so that's going to equal v squared. All right, so what did I do there? I hope I didn't go too fast, but basically I had this number right here. There it is. I multiplied both sides by 10 to the positive 27, and on this side there's the positive 27, but that will eliminate that, and then I divided both sides by 1/2 times 6.68. There it is there like that. Okay, now that is going to be times 10 to the exponent 27 minus 21 is 6, like that, divided by that. Okay, however you want to do it on your calculator. It's just that my calculator right now is doing a very funny round off. I think I know how to fix that, but I don't want to be bothered wasting your time. All right, so let's just see what that's equal to. That's equal to this number right here. That's equal to v squared. And so v is equal to, let's take the square root of that, meters per second. Okay, so you know, 1.3435 kilometers per second. Okay, so at 20 degrees Celsius, what is this all saying? So at 20 degrees Celsius, this is how much kinetic energy a particle has. Okay, now if that particle is helium with an atomic mass of 4 AMUs, then that would correspond to a velocity of 1.35 kilometers per second. That seems pretty fast, but that's because helium is really small. Okay, then so that's why you get 1.35 kilometers per second. In 1 second, at 20 degrees Celsius, a helium atom will travel over a kilometer. Okay, so that's pretty fast. Now, our atmosphere is actually made up of oxygen and nitrogen, okay, which have, you know, much higher atomic masses, okay, like 28 and I forget the other one right now. But, you know, at those atomic masses, you're down to about 300 to 400 meters per second. And that kind of makes sense because that's around roughly the speed of sound, you know, 340 meters per second. So that, you know, the speed of sound and the speed at which the molecules are moving are roughly the same, and you're getting that out of this temperature analysis. Okay, so I should have done that first before going to this, but it leads directly into that, because what this says is if you add energy to an object, you're going to speed up the molecules, okay, because if you increase the temperature, you speed up the molecules. Okay, so adding heat to something increases the temperature, except at a transition, okay, a phase transition, like between ice and water. So when you're at ice at 0 degrees Celsius and you add heat to the system, you don't get ice at 1 degree Celsius or ice at 2 degrees Celsius. You start to convert the ice to water at 0 degrees Celsius. So there's a latent heat, and that latent heat is the heat that it takes to just transition from ice at 0 degrees Celsius to water at 0 degrees Celsius. Okay, and so let's do a problem with that. Okay, now there's lots of different problems here, but I'm just going to do one of them because I don't think it's worth, you know, laboring over a lot of different variations. How much energy does it take to heat up, let's say 50 grams of ice at negative 10 degrees Celsius to water at 10 degrees Celsius? Okay, so we're going to start with ice at 50 grams of ice at negative 10, and we want to get to water at 10 degrees Celsius. Okay, so there's actually 3 steps here. The first step is ice from negative 10 degrees Celsius to ice at 0 degrees Celsius. Okay, and for that one, you're going to use this formula right here. Okay, because that is basically just adding energy and the temperature goes up. You're still ice. You don't have a phase transition. So you go from ice at negative 10 to ice at 0. The second step is you're going to go from ice at 0 to water at 0 degrees Celsius. For that formula, it's a phase transition. Notice the temperature doesn't change, but the phase changes. Use this formula here. And then finally, you're going to go from water at 0 degrees Celsius to water at 10 degrees Celsius. Okay, and for that one, you're back to this. Okay, so when the phase doesn't change, adding heat changes the temperature. Use the formula that I've highlighted there. When you're at a phase transition, the temperature doesn't change, but the phase does. In other words, you go from like solid to liquid or liquid to gas. Okay, and so there's 3 steps here because you're starting from the ice at below melting. You get it to ice up at melting, then you melt the ice, and then you got water, and then from water at 0 all the way up to water at 10. Okay, and sorry, I just looked over at my dog there. All right, so let's do that. Number 1 is we use this formula here, call that Q1, and the mass is 50 grams, which is 0.05 kilograms. The specific heat, you got to watch it. There's a specific heat for water, and there's a specific heat for ice. Okay, and the specific heat, the 2 are different. Okay, so the specific heat, let me just, there it is. Okay, you can see it now. Okay, and so we're in ice, so we're going to use this number right here. Whoops, so went too far. Right there. Okay, so the mass was 0.05 kilograms. 50 grams is 0.05 kilograms. The specific heat is the specific heat of ice, and the temperature change is, well, how much did I heat it up? I went from -10 to 0, so the temperature change is going to be 10 degrees Celsius, okay? All right, so what's that work out to? Q1 is going to equal, just rewrite this. Notice how the units go. The kilograms here will cancel the kilograms in the denominator there, okay? And the degrees Celsius there in the denominator cancels degrees Celsius in the numerator there, and your only remaining unit is going to be joules, okay? So it works out. So the answer will come out in joules, and that number is going to be 1,075 joules. Okay, great. That's number 1. Q2 is going to be this one. It's the mass, 0.05 kilograms. Okay, multiplied by the latent heat of, and there are 2 latent heats. There's latent heat of fusion, which is the ice-water transition, and latent heat of vaporization, which is the water-steam. Whoops. Well, what are we doing here? We're going ice-water, from ice to water, so we want that one. Okay, so make sure you choose the correct one, because if you choose that one, you'll get the wrong answer. Right? So we want to go from ice to water like that. And there is no temperature change. It's just M times L. Okay, so there's M and there's L. Be careful. This is kilojoules there. Okay, and so we got a kilogram there. That'll cancel the kilogram there. But your answer is actually going to come out in kilojoules. Okay. And so what's that going to equal? Do that in a second. Like that. Okay, now you got to watch it. This was joules and that's kilojoules, so when we go to add them, we better make sure that we're working in the right units. In fact, we can switch this one over to kilojoules right now. Okay, what did I do? I moved the decimal over 1, 2, 3, and that would give me this. Whoops. There we go. And I'm just rounding that 7.5 up to 8 like that. Okay, so there's the energy to heat up the ice to melting. This is the energy to melt it. And then finally, we want to heat the water up. And so it's this one right here. Okay. And now it's the same formula as above here like that. But now for the specific heat, we want the specific heat of water, not ice. And the specific heat of ice, sorry, the specific heat of water is 4,186 joules per Kelvin. And the temperature change, that one was 10 as well, because we're going from 0 to 10. Okay, so 0 to 10 like that. All right, and Q3 here. The kilograms will cancel out. This is the same cancellation as we got before. The degrees Celsius will cancel out. And your answer will come out in joules, like that. Okay? All right. And so what's that going to work out to? (2,093 joules, which we'll write in kilojoules, 2.09 kilojoules, like that. Okay? So what's the total energy required? Well, it's going to be the energy to get the ice up to 0 Celsius, plus the energy to melt the ice, plus the energy to heat up the water. Okay? Which one took the most? The melting. The latent heats are usually much bigger than the other heats. Okay? All right, so what's that going to equal, just to finish off that problem? Whoops. 19.9 joules. Let me see if I messed up the... No, I didn't. Okay. All right, there we go. Okay, so there we go. That answers that question. Okay. Now, I did do a problem with mixing of two materials. I'm not going to do one right now because you had one on the assignment, and you also had one on the in the lecture. The pre-recorded lecture. So I don't want to do one of those. They're a bit complicated too, but I don't want to overdo this because there's a lot of well, we're already an hour and a half, so I don't want to overdo it. But if you do want to see one, still, my office hours, you can always ask me to do an example of that. Let me take a look in the chat here. All right. Okay, so almost done with thermodynamics. The last part of thermodynamics was the third law of thermodynamics. So the first law of thermodynamics is energy is conserved. Okay, and that means if energy during any process, if you add up all the energies, including the heats, which we didn't know about last semester, energy is conserved. Okay, so if you put a hot object near a cold object, nothing might be moving. You may not see anything moving, but heat is leaving the hot object and going to the cold object. And if 10 joules leaves the hot object, then 10 joules must go into the cold object. Okay, you can't have 10 joules leaving the hot object and only 5 going into the cold. You're going to say, well, where'd the other 5 go? Okay, energy is always conserved. Okay, so that's the first law. Energy is always conserved. The second law, though, says something a little bit more. It says that whenever you got a process, okay, let's do this one first. You have a process where heat is being transferred. The heat will always go from hot to cold spontaneously, never the other way around. Okay, so you could put two objects together. If you can have the hot one losing 10 joules and the cold one gaining 10 joules. That's okay, but you can't have the cold one losing 10 joules and the hot one gaining 10 joules. That wouldn't violate the first law because still it's 10 joules transferred. One thing loses 10, the other one gains 10. That's okay. But the second law says no, the heat will only flow from hot to cold, never from cold to hot. Okay, so that's one thing, spontaneously. All right, that's without the intervention of some other mechanism, which I'll discuss in a second. The other statement of the second law is that work can spontaneously become heat, but not the other way around. That's friction. Okay, so if you do work like you rub your hands together, they'll warm up. Okay, so that's work, the work you're doing by rubbing your hands becoming heat. Never you're going to have heat turn into work. Okay, there's a lot of heat, in the objects around us. So there's a lot of heat, say, in the table here. And I have a mug here. The mug is sitting on the table here. So there's a lot of heat in the table here, represented by my hand. Would that heat ever magically come into the mug and make the mug jump up into the air? No. The mug could fall and heat up the ground as it falls because of friction, but never could the heat that's in the ground make things pop up into the air. Okay, so the second law of thermodynamics is directed in time. It says processes will go one way but not the other way. Okay, and at the microscopic level, you can understand that as going from an ordered system to a disordered system. Okay, and it's beyond our course to really go into the details of how that works, but it's actually quite rigorous. Okay, it's It's called statistical mechanics, and you can calculate very exactly what is meant by order and disorder. Okay, so it's not; these are not just qualitative words. You can actually put quantitative quantities to them. But qualitatively, in this course, we can understand it in this way: heat will spontaneously become work, but not the other way around, and heat will spontaneously travel from hot to cold, but not the other way around. Spontaneously means you can make it go the other way, but only under a very special circumstance, and you can make heat become work in a heat engine, but it only becomes work because heat is trying to go from a hot area to a cold area, and in going from this hot area to a cold area, some of that heat might become work. Okay, not all of it, but some of it might become work. And you say, well, can you give me an example of that? Yeah, like if you got like a hot source here, and it heats up the air, and then the air goes up. All right, as the air is rising, as the hot air is rising, it can turn a little pinwheel. That's heat in this source turning into work as that pinwheel turns. Okay, now the heat says, I'm not trying to make work, I'm just trying to go from a hot area to a cold area. But in going from that hot area to a cold area, a little bit of that energy can be siphoned off and become work. Sadi Carnot discovered that this is the limit of the efficiency right there. Okay, the efficiency, the maximum efficiency, the maximum amount of energy that can be converted into work is given by that formula. You can't get more than that, otherwise you have a violation of the second law. Okay, now where that formula comes from, again, beyond the scope of the course, but there it is. There is a limit. Okay, and what is the true efficiency? So this is the maximum efficiency. We usually call it EC for Carnot efficiency, but we could just call it maximum efficiency. Okay, and it's not. Fix that. It's not that you can build something better. It's not a technological limit. It is actually a physical limit. Okay, you simply cannot build a device which does better in terms of efficiency than that. Okay, so it's this maximum. The true efficiency is this. It's how much energy did you absorb in heat from the high energy, or I shouldn't say absorb. How much energy did the hot give you in joules, divided by, the amount of work divided by how much energy the hot area gave you. So if the hot energy area gives you 100 joules and you convert 30 of that into work, well, you got 100, you converted 30, that's 30 divided by 100, or 30%. Okay, so 30% of your energy that comes from the hot area can becoming work would be an efficiency of 30%. And that's what this formula is. This formula is just basically the definition of what you mean by efficiency. It's how much work do you get per joule of heat that the hot area gives you. Okay, that quantity there can never be bigger than the max. In other words, E must be less than E max for all real situations. Okay, so very simple problems. Let's do this. So an engine runs between boiling water and freezing water. Okay, so those are your two temperatures. If during one cycle, because these engines run cyclically, like a heat engine like your car is a heat engine, it's got a piston in it, just cyclically converts heat into work. Okay, if during one cycle 100 joules of energy are delivered from the boiling water, what is the maximum that can be converted into work? Okay, so let me just read that again. So a heat engine is running between boiling and freezing water. Okay, that gives you your high and low temperature. Okay, if during one cycle 100 joules of energy are delivered from the boiling water, so the boiling water is going to give you during one cycle 100 joules. How much of that? What's the maximum that can become work? Well, it can't be 100 joules. That would violate the second law. Okay, and it can't be more than that Emax. So let's work it out. So first of all, what is Emax? All right, and I'm gonna call it again EC for the Carnot efficiency, just because everyone else does. Okay, but again, Carnot efficiency, maximum efficiency, they're synonymous. Okay, so here we've got that this is equal to 1 minus, and we have to be really careful. Okay, the low temperature is water freezes. Water freezes at 0 degrees Celsius, but this formula here depends, everything has to be in Kelvin. So the temperatures must be in Kelvin. Okay, so for the low temperature here, we're going to put in 0 plus 273. And for the high temperature here, we're going to put in 100 plus 273. Okay, so what did I do? This is the temperature at which water freezes. 0 degrees Celsius converted into Kelvin is 0 plus 273. The temperature at which water boils is 100 converted into Kelvin, and so you add 273. Okay, so what's that number equal to? Well, this number is equal to, write it down here, EC is equal to this number right there. Okay, now the number always has to be less than 1, okay, because it's a fraction, and you can convert it actually to a percentage. So we could say 26.8%, like that. Okay, so what that is saying is that at most, out of all the energy you absorb from the boiling water, only 26.8% can become work. In reality, it'll probably be even less than that, because there's also technical deficiencies in your heat engines. But just as far as the physical limit, because of the second law of thermodynamics, you're not going to get more than 26.8%. Now, this has to be true, okay? And we've already determined that this maximum is that. And so with that E there, for the E, we can write in this. Okay? The work, the ratio of the work to how much energy is absorbed from the high has to be less than that 26.8%. Now, the amount of work during one cycle, the amount of energy that's absorbed during one cycle is 100 joules. So we could write in for Q high that. Okay? Now, if we multiply both sides by 100, we'll get that W has to be less than 26.8 joules, like that. So during one cycle, 100 joules is absorbed, or delivered is probably a better word, delivered by the boiling water, and only 26.8 joules at most, because it could be less but not more, is converted into work. Okay, so there you go. There's a heat engine for you. All right, and an example of the second law. So the second law is mathematically pretty easy, but it's a little bit conceptually demanding. Okay, you have to imagine, like what's going on in the situation in terms of a heat engine. Okay, so we're done with thermodynamics, and let's continue. Okay. And the next part is, so remember, we're not doing the voltage, current, capacitor stuff. We're just going to do that introduction to electricity stuff. And there, all I went over, let me just tell you before I actually jump in and do problems. I talked about the electrical force and the magnetic force qualitatively, okay, in comparison to the other forces. We did Coulomb's law, and we also did electric field and electric potential. Okay, electric potential is synonymous with voltage, but generally we use the word voltage when we're talking about circuits, okay, which is the topic that's not on the test. Okay, so you do need to know something about qualitatively where electricity is in the family of forces. There are 4 fundamental forces in the universe, and traditionally, because we've been unifying them, so not to make life too complicated, there's just, you can think of the universe as being 4 fundamental forces. Remember, a force is a push or a pull. Okay, so whenever something is pushing or pulling on something, it's one or a combination of these fundamental forces. So the word fundamental means that there's nothing more deeper than them. Okay, so what are they? Well, one of them is gravity. Gravity is a fundamental force of the universe. Gravity isn't made up of other forces, okay, at a deeper level. Gravity is its own fundamental force. Okay, and the other one is electricity and magnetism, okay, together. And that's a little subtle, but by the end of the course, you'll see that electricity and magnetism are more related than you know right now. Okay, the other one is the weak nuclear force, and the other one is the strong nuclear force. Okay, we're not going to study the weak and strong nuclear force, but you do need to know where you see them. The weak nuclear force, that's like whenever you have like radiation therapy, for cancer, they do radiation therapy. Uh, Anything that's radioactive is mostly due to the weak nuclear force. The strong nuclear force is exactly that. That's like atomic bombs, okay? When you see nuclear explosions, that's really the strong nuclear force or nuclear reactor. So strong nuclear forces like atomic bombs or nuclear reactors. The weak nuclear forces like radiation, like from radiation therapy and stuff like that, okay? Electricity and magnetism, well, you kind of know what electricity is now, and gravity. You certainly know what gravity is because you experience it all the time. You're being pulled towards the earth, okay? Now, uh, what's the similarities and differences between these? So you should know that gravity is purely attractive. There's no such thing as anti-gravity that we know of. No one's discovered it. If you discover anti-gravity, that's two masses which actually repel one another, you will most certainly win the Nobel Prize. You'll be just like amazing. Okay, it'll totally confuse physicists all around the world. Okay, so gravity is purely attractive. Electricity is both attractive and repulsive. Okay, now of all the forces, gravity is the weakest. And yet, it's the one that holds everything together because gravity, being only attractive, can only build up. Okay, so it's like you've got so much gravity, and then you add more mass, it can only go up. It can only go up. So the entire solar system is being held together by gravity. The whole entire galaxy is being held together by gravity because gravity is positive. It's like adding a bunch of positive numbers. You can only go up. You can't go down. Okay, so but with electricity, you got both positives and negatives. You got both attractive and repulsive. And so if you add something, it might be attractive. You add something else, could be repulsive. And so you have a combination of attractive, repulsive, attractive, repulsive, attractive, repulsive, and they tend to cancel one another out. Okay, and that's why even though this mug, has a lot more electrical forces associated with it, there's probably more gravitational pull between me and the mug than there is electrical. And you go, why? Well, because my electrons and protons are simultaneously being attracted and repelled from the electrons and protons here. So there's attraction, repulsion, attraction, repulsion. They tend to add up to zero. That's called screening. That's this business of like it's adding up to zero. Whereas the gravity is it just adds, it just adds, it just adds, it just adds. Okay, so that's the difference between the two. The weak and the weak nuclear forces and the strong nuclear force, they're also both attractive and repulsive. And so gravity is unique that way. Gravity is unique that way. It's the one that, even though it's the weakest, it's the one that builds up and holds the entire universe together. Okay. All right. Now, I just said a minute ago that electricity and magnetism are related, but they're related in a complicated way, in a sort of a prima facie, or a simple way of thinking about this. They look like they're different because electricity works with positive and negative charges, and magnetism works with north and south poles. And north poles don't seem to have much to do with negative and positive charges, and south poles don't seem to have anything to do with negative and positive charges. So it's not like north is positive and south is negative, or vice versa. They don't seem to work that way. And also, if you have like charges, you can separate them. So if you have a helium atom, you've got like an electron and a proton, you can split them apart. You can pull the electron off, and you can have a bare proton and a bare electron. It'd be hard to do, but you could do it. But you can never separate north and south. You say, well, what do you mean by that? What do you mean you can't separate them? If I have a bar magnet here and I split it in half, don't I have a north here and a south there? No. When you split it in half, each of the pieces will have a north and a south. And you say, well, I'm going to split it in half again. Well, then each of those two pieces will have a north and a south. Whenever you have a magnet, there's a north side and a south side. You try to split it, you can have both of the pieces are both going to have a north and a south side. So you cannot separate poles, but you can separate charges. So there's two ways in which electrical force and magnetism are different. One, electricity works with positive and negative charges. Magnetism works with north and south poles. And charges are separable, poles are not. Okay, so we'll see more why. All right, whenever you've got bare charges, they are attracted or repelled by one another by this formula right here. That's Coulomb's law, okay? And there is the Coulomb constant right there. All right, so let's do a very simple problem with that. And there's not really much you can do with that. Let me take a look in the chat, make sure that everything is still okay. I've been a little bit traumatized by, speaking for 20 minutes without anyone hearing me. So, okay. All right. So let's say a positive 3. Let me get a micro from my... So the MKS units are coulombs, but generally a Coulomb is very big, so you tend to work with microcoulombs. A +3 microcoulomb charge is placed, I don't know, let's say 15 centimeters from a +5 microcoulomb charge. Okay, so two questions. Is the force attractive or repulsive? Okay, and how big is the force? Well, what is the magnitude of the force? All right, so is it attractive or repulsive? Well, like charges repel. Okay, so they're both positive, so the answer is repulsive. And it's unlike charges attract. Okay, they repel because they are both positive. Okay, most people know that. That's pretty easy. But the rule is basically if the two charges are the same, they repel. If the two charges are opposite, they attract. Okay, so opposites attract. All right, and these are not opposites, so they are repelling. Okay, what's the magnitude of the force? We'll use this formula right here. Okay, and K, that's your Coulomb's constant. Here it is in MKS. It's a big number. It's 8.99 times 10 to the 9. Okay, Q1, we will put in 3 microcoulombs. At this point, we don't really need the positive signs because we know it. We already know it's a repulsive force. Okay, and then over here we're going to put the 5 microcoulombs like that, and for R we're going to put in 15 centimeters. Okay, well, so far so good, but everything's got to be in MKS. Okay, well, the constant here is MKS. Okay, there it is right there. If that constant is MKS, then everything else has to be MKS. Now here we have micro, and you say, well, what's micro? Micro is times 10 to the -6. Okay, so times 10 to the -6. And there's another, whoops, what I do? There's another micro right there, so there's another times 10 to the -6, like that. Okay, and let's get rid of these coulombs because now we're in MKS. And the other one is centimeters. And centimeters is, so if you got 15 centimeters in meters, that's 0.15 meters. Okay, so we have to convert that to meters. Now everything is in, oh, 1 second. Excuse me 1 second. Hello? I apologize. Real life, right? That was for a vet appointment for my dog. Okay, very important. He's not doing too well, but not to get too personal. I just feel that I need to apologize as to why I had to take that. Normally, I would just drop a call. Okay, so let me just take a look in the chat here, and okay, so now everything is in MKS, and for those of you who were like on my live streams last semester, most of you were, you'll remember his picture, and that's going to equal, it's turned out to be a very nice number here. It's actually about 6 newtons, so the force would be 6 newtons. Okay, I used to use his picture for the intro, okay, for the beginning of the stream. Okay, so so there's the answer. It's 6 newtons and it's repulsive. Okay, so the way you would see this on a test, I would probably, because it's multiple choice, I might have one would be like 6 newtons attractive And then I would have another answer was like 6 newtons repulsive. And you want to choose that one, okay? So what I'm testing you is both can you work with the formula and do you know whether it's attractive or repulsive, okay? So there you go. These are pretty easy. And also you could see that 6 newtons is a kind of a reasonable force. So you know when you have like microcoulombs in the lab and they're separated with centimeters distances, you're looking at roughly a newton worth of force. If these were coulombs, then it would be not only like 10 the 10 to the minus 6s wouldn't be there, but it would be 2 10 to the minus 6s that aren't there. That would be an increase by 10 to the 12. That would be trillions of newtons. You wouldn't be able to hold such a thing together. It basically would explode because the electrical forces would cause the thing to explode. Okay. All right. Last question. Very long stream, I know, but a lot of material here. This formula here relates force to an electric field. An electric field, the way you should think about it is that there's some charges out there and they create a region of space with an electric field. If I put a third charge or another charge, a test charge as it's called, in that electric field, it experiences a force. The force that it experiences, how big is the electric field? Multiplied by Q, that'll tell you the force, okay? The other one is that there's a relationship between the potential energy, because if there's a force and you let go of something, it's going to fall. Okay, but fall, we usually talk about gravity, but it's going to move towards one of the ends of one of the areas, okay? And so you could think of that as a kind of an electrical falling. And that falling means that there's a potential energy associated with this object, with this charged particle. And the potential energy that's associated is the size of the charged particle multiplied by the potential. And that kind of defines potential for you, okay? And then finally, when you're in a region of space where there's an electric field, the further you go out into that electric field, the more the potential is, okay? Now that's a bit abstract, so let's do a problem with this, and I think it'll make it a lot clearer, okay? And so actually, let me show you a picture that I prepared. Here's a picture. There are two plates here. So you've got one plate at 10 volts and another plate at 0 volts. The 0 volt is usually like the negative plate, and the 10 volt here is the positive plate, okay? And I've put these two plates 10 centimeters apart, okay? And I'm going to put oh, I didn't say centimeters here. Let me just fix this. This is centimeters here like that. Okay. I put this electric charge here, which is this negative electric charge, negative minus 2 microcoulombs. Okay. I've put that in a region of space here. And it also has a mass of 1 microgram. Okay. So like a droplet of water, negatively charged droplet of water. It's 3 centimeters from the positive plate. So when I let go, what's it going to do? It's going to fall towards that positive plate. It's going to be attracted towards that positive plate, and it's going to hit it. Okay, so there's our situation, and now let me ask some questions about that. All right, so over here, the first question is with reference to the diagram. What is the electric field between the two plates? Okay, so what's the electric field between the two plates? You go, well, how am I going to solve that? So the electric field, you could either use this one or that one because they're the only two that have electric field. But this one relates electric field and force. Okay, so if you knew the electric field, you could calculate how much force there was on that negative 2 microcoulomb charge. Okay, but you don't know the electric field. You're trying to find it. You don't know the force. Okay, so that's not going to work. But this one will. Okay, right there. Okay, so this one, what does it say? It says, whoops, it says basically the electric field is related to the potential multiplied by the distance that you travel into the field, okay, or into the potential. Now, we're trying to solve for E, so I can just rearrange this and do this, okay? So I used H here, but you know what? I mean, H, D, I don't know. Maybe we should change it to D. Not that it makes that much difference, okay? But I don't want you to think about it as a height up and down. It's more like just a distance that you go into the field. I think in my notes I called it H, but it doesn't matter. Just think of it as the distance that you've traveled into that field, okay? So if the total distance across, let me show you the picture again. If the total distance across is 10 centimeters and the total potential across is 10 volts, then you've got 10 volts per centimeter, 10 volts per 10 centimeters, okay? So over here, the voltage, the top part is going to be 10 volts. The bottom part is going to be 10 centimeters like that. And so you get 1 volt per centimeter. Okay, now that's not MKS, but I'm going to leave it like that just for a second because this is how you should think about electric field. Basically, the electric field is 1 volt change for every centimeter that you go into this field. Okay, so let's go back to the picture. If we're at the 0 volt plate, here, okay, you're at 0. If I walk 1 centimeter over, I'm at 1 volt. If I walk 2 centimeters over, I'm at 2 volts. If I walk 3 centimeters over, 3, 4, 5, 6, 7, 8, 9, 10. Okay, for every centimeter that I walk in, okay, so like here, I've walked in 1 centimeter. I went from 0 to 1 volt. I walk in another centimeter. I'm now at what? 2 volts. I walk in another centimeter. Another centimeter. I'm at 3 volts. Okay, does that make sense? So that's what electric field is. It's like how much voltage do you increase or decrease for every step that you walk into the field. Okay, 1 volt per centimeter. Now in MKS, because probably on the test I'd want the answer in MKS. Well, I made the numbers easy on purpose here. Just so you would, it really help your intuition. 1 centimeter is 0.1 meters, like that, and that would be 100 volts per meter. Okay, now that's true. That's the same, 100 volts per meter. But you know, we don't even have a meter's worth of distance in there. It's only like 10 centimeters. Okay, so it might be just you know, even though this isn't MKS, that might be a more intuitive way of thinking about it. Okay, great. There's our first question. The second question is, what is the potential energy of the -2 microcoulomb charge? Okay, so you say, well, how do I calculate that? That's this formula here, but we got to be really careful with that one. Okay, it is -2 microcoulombs, all right, for the charge, for Q, but what's the V? What voltage do you put in there? All right, let's go back to that diagram and take a look. It's a negative charge, so it's not going to go from there to the negative plate. It's going to go away from the negative plate and towards the positive plate. Okay, so it's actually going to travel 3 centimeters across the to the positive plate. Okay, so let me just emphasize that. Let me I don't know, let me do it in purple. I'll rub this off in a minute, but just so you can see it here, that's the distance. Whoops, that's messy. That's the distance it's traveling right there. You see that purple line in there? That's the distance that it's traveling. Okay, now if it were positive, I'll show you that one in a minute. That's how far you know, it would go the other way, but it's negative, so it's going to go to the positive, so it's going to travel 3 centimeters. Okay, it's traveling 3 centimeters in a field which is 1 volt per centimeter. So what's the voltage difference between the two? Well, the voltage difference between these two here, from there to there, would be 3 volts. Okay, does everyone get that? Okay, because it's a volt per centimeter. Every centimeter that you walk, you're traveling 1 volt. So from there to there, that's 3 centimeters. Okay, and so 3 centimeters corresponds to 3 volts. And so the number that you would put in here is, and this is a typical mistake that's made, it's not 10 volts, it's 3 volts. Okay, well, and maybe just to be very clear, like on the test I'm clear, but you know, in right here right now, to be very clear, what is the potential energy of the with respect to the positive plate? Okay, like that. All right, because it's not going to fall to the negative plate, it's going to fall to the positive plate. Okay, well, bit of an aside, what if I given you a positive charge? Okay, what if I given you a positive charge? So let's go back to this. If I given you a positive charge, okay, and not to make the diagram too messy, let me see if I can put a positive charge right here. Where would it fall? It would fall this way. And how far would it fall? 7 centimeters, and 7 centimeters would correspond to 7 volts. Okay, so just be careful that you're looking to see if you've got a positive plate, a positive charge, or a negative charge, and then see which plate you're falling to. If you're falling to the one plate, just measure the distance. Okay, so the negative charge travels 3 centimeters. Every centimeter is a volt, 3 volts. Okay, the other way, if it were a positive charge, it would, at the same point in space, it would travel 7 centimeters to the to the 0 volt plate, and so 7 centimeters would correspond to 7 volts. Okay, so let me rub that off to make my diagram clean again. All right, okay, so let me know in the chat if that's confusing to you, but I think it's pretty clear. Okay, and it also what I'm trying to do, like I said, the numbers are simple, but what I'm trying to do here is really show you what this is telling you. That is telling you, the electric field is telling you how many volts do you change for every unit distance that you travel. And the potential energy is, okay, well, you're at a voltage. Well, how do you know that voltage? Well, how far would you travel until you've exhausted your fall? Okay, whatever distance you travel, that corresponds to some voltage because of the E is equal to V over D. Okay, so well, I'm at 3 volts, so or the negative charged particle is at 3 volts. Okay, because it's going to fall 3 volts to the positive plate, and then multiply that by the charge, which is -2. And by the way, for this problem, you don't really need the negative, because the negative and positive for these problems are all about whether it's attractive or repulsive. So we don't need that, but we do need to change that micro to times 10 to the -6. Okay, and now we can get rid of the Coulomb and the volt, because a Coulomb times the volt is, guess what, a joule. Okay, and if we work this out, this is going to equal 6 times 10 to the -6 joules, like that. Okay. All right, so there's the potential energy. There is the potential energy of that charged particle. Okay, just like, if you have a ball up in the air and you let go, it's going to fall, and it has potential energy mgh. Here, this thing has potential energy Q times V, where V is E times D. Okay, all right, great. Now what? Well, let's ask another question. With what velocity would the charged particle hit the positive plate? Okay, so with what velocity would the charged particle hit the positive plate? All right, so let's think about this. That's the potential energy. When the charged particle, let me show you the picture again. So over here, let me see here. Yeah, over here, where my cursor is, it's all potential energy. By the time it hits the plate, all that potential energy converts to kinetic energy, and so we can say that 1/2 mv squared will equal the potential energy. Okay, because all of that energy is going to be converted to kinetic. Okay, now M, I told you what M is. Okay, if we go back to the diagram, I said that M was 1 microgram. Okay, so M over here is 1 microgram. So let me just rewrite this formula here. For that M, I'm going to put in 1 microgram. Well, you know that micro is times 10 to the -6. Like that. Okay, so this number right here, that's microgram. Let me get rid of the joules here. Everything is in MKS. Okay, so that's 1 microgram is 1 times 10 to the -6 grams. Okay, there's the half because it's 1/2 mv squared. There's the v squared. Okay, and now we can solve. All right, well, next line, 10 to the -6 on this side. We'll divide out 10 to the -6 on that side. That's why I chose the micro. Okay, and now I've got a half on this side and a 6 there, so v squared is going to equal 12. And if you take the square root of 12, you will get, what will you get? I'll find out. Square root of 12 is 3.46. And what's the MKS units of velocity? Meters per second. Okay, so there you go. We've covered everything. Some variations on problems I didn't do, but that's pretty much it. Okay, so let me look in the chat here, and let me ask. Yeah, we went 2 hours, which is what I expected. Okay, let me just say here: is everyone okay? All right. I mean, you may not have any questions right now because this, 2 hours of problem solving is a little overwhelming. But if you have problems, if you go over this and you have problems, you can always catch me in the office hours this evening. Otherwise, we're done. Uh, all right, Matt. I apologize so much for that 20 minutes. When I email, I'm going to email everyone and just say, start from a little later. I know I went a little bit quicker there, but I mean, if you watch this from where I finally get the mic working, it should be okay for people. But the the um, the joys of technology, right? All right, then I don't see anyone else asking questions. I'm just going to say goodbye, and again, if you have any questions, email me or whatever. Okay, bye bye.